All right, we're going to continue with section 14.8. And one thing I neglected to mention in our previous video is you may think that, especially when you see a U in an integrand, which was we had in our last example, that you have to do some kind of back substitution. But remember, this is just like polar coordinates or cylindrical coordinates or spherical coordinates. We're not going to switch back from that change of variables to whatever we originally had. So there is no like back substitution or anything that's necessary here. You just go ahead and evaluate your integral as is, and you have your final answer to the problem. So I'll reiterate that again once we get to the end of the example that I'm going to work on in this video. So we're on page 968, and we are going to look at number 18. Number 18 says in exercises 18 through 25, evaluate the integral by a suitable change of variables. So here again, we have to figure out the change of variables ourselves. They don't give us what the change of variable is that we should use. And 18 says the double integral over R of 49x squared y dA, 49x squared y dA, where R is the region bounded by the lines 2x minus y equals 1, 2x minus y equals negative 2, x plus 3y equals 0, and x plus 3y equals 1. So let's go ahead and sketch our region. This we can see from the integrand. This doesn't look like, in contrast to our last problem, it doesn't look like it would be troublesome to evaluate this just solely based upon the integrand alone. Let's see what the region looks like. All right, so first line we have 2x minus y equals 1, and then 2x minus y equals negative 2. So 2x minus y equals 1. So we're going to have, this is not going to be drawn to scale either, but we're going to have something like this. And that was 2x minus y equals 1. Make sure I have my line correct. Yeah, okay. Then we had 2x minus y equals negative 2. So that would take us, say about right here. So this is 2x minus y equals negative 2. And then we have x plus 3y equals 0. So x plus 3y equals 0. And x plus 3y equals 1. What was that? I think that was 2. These probably aren't crossing in the proper places, but we just want to get an idea of what this looks like. X plus 3y equals 1. Yes. So our region R is that region right there, which we notice that's neither a type 1 nor a type 2 region. And we would have to, if we wanted to make it either type 1 or type 2, we'd have to split it up into multiple regions to do that. This one looks like you have to split it into 3 regions. Might be the only way to do that one. All right, so that's our region R. So now what we do is we need to set up a change of variables, define U and V based upon what we see here or what we see there, or a combination of the two. We don't see any major issues here, but notice here on all of these, we see that they kind of set us up with the x plus 3y and the x plus 3y. So they set us up nicely with regards to defining our transformation and the 2x minus y and the 2x minus y. So I'm going to let u be equal to 2x minus y and v be equal to x plus 3y. And if you chose the opposite of what I chose, you still will get the right answer at the end. So it doesn't matter which way you choose your u and your v. So now we want to sketch not the region R, we want to sketch the region S and see what our bounds are in terms of u and v. So what do we get from what we have? We have x plus 3y equals 0. What does that tell us? That tells us v equals 0. And then x plus 3y equals 1. Tells us v equals 1. 2x minus y equals negative 2. That tells us u equals negative 2. And 2x minus y equals 1, which tells us that u equals 1. So now we have our bounds for u and v. And we'll sketch the region as well. So the bounds for u and v are v varies between 0 and 1, and u varies between negative 2 and 1. So now we sketch that region in the UV plane. Negative 2 and 1, okay. So u is between negative 2 and 1, and v is between 0 and 1. So that's our region S, a region over which it is fairly easy to integrate. So now what we need is we need our Jacobian, because we need that as the last aspect of our integrand that we're missing, with the exception of to find the Jacobian now. In the last problem, we didn't end up having to solve this system for x and y to find the Jacobian. And we don't have to solve the system for x and y to find the Jacobian in this problem either. We can find it the same way we found in the last problem. But one thing to notice here is that we need this integral to be in terms of u and v. And there's an x in there and a y in there. So before in our last problem that we did, this is what appeared in the integrand, whatever we had right there. And that's what appeared in the integrand. So it was very easy to do the substitution. But now notice we need x to plug in right there and y to plug in there. So we can't avoid solving the system for x and y. So in the procedure that we did, or we're using, this would be step one. Step one. I think part of it was, this next step was the picture itself of S, which was step 2. So that was step 2. Step 3 we didn't use in our last problem, but we're going to have to use it in this problem. Step 3 is we need to solve this system for x and y so we can plug them back in there at the end. And since we're doing that anyway, we'll just use, we can use x and y to find our Jacobian, although actually it could be easier to find the Jacobian with these, but I'm going to do it the other way because you haven't seen it that way yet. All right, so step 3 is we're going to solve the system u equals 2x minus y, v equals x plus 3y for x and y. And don't let this system concern you in solving for x and y, given the fact that there are u and v in there. So that tends to be the sticking point for people. But u and v are just like any other constants, and you can treat them as such when you go through to solve this system. So you can use elimination, substitution, whatever it is that you want to solve. Just you have to constantly keep in mind as you're going through and solving the system that I am trying to solve this for X and Y. So if I'm going to do substitution, I would solve, like, say, for instance, this second equation for Y and substitute it in there, or for X and substitute it in there. The U and V aren't your variables anymore. All right, so I'm going to do elimination. That's just because I feel like it's easier. So I have the two equations, U equals 2X minus Y, and I'm going to eliminate the Y's, or I'll eliminate the X's. To eliminate the X's, I'm going to take my second equation and multiply it by -2, and then I'm going to add the two equations. So when I do that, I'll get -2V equals -2X, and then minus 6Y. Add these two equations now. And I'm going to get U minus 2V equals, the X's will go away. And then I have Y minus 6Y, so I end up with -7Y. And remember, we're trying to solve for X and Y, so all I need to do here is divide both sides by -7. And I end up with Y equals 2V minus U over 7. And now I need to solve, take this and put it back into one of those equations to get our X is. So putting this back into that first equation up there, we end up with U equals 2X minus 2V minus U over 7. Move this to the left and find the common denominator will be 7. So I'm going to get 7U plus 2V minus U over 7. 7U plus 2V minus U over 7 equals 2X. And so we get 6U plus 2V over 7 equals 2X. And divide both sides by 2, that gives us X equals 3U plus V over 7. So now we have X and Y. And these are what we would substitute back into our integrand, but we're still missing our Jacobian. So now you have the option of using these to find your Jacobian, but you have to make sure you do the reciprocal of whatever you get when you use those, or using these two things to find your Jacobian. You don't need to do the reciprocal. Either way, make sure you do that. Put the absolute value of the Jacobian in your integrand. I'm going to do it using these this time, although those are easier because they don't have the fractions in them. But just because we've already done it using U and V, I want to make sure we see how to do it using X and Y. So the Jacobian, so J of UV, remember, is going to be the partial of X with respect to U, partial of X with respect to V, partial of Y with respect to U, partial of Y with respect to V, taking the determinant, that determinant. So the partial of X with respect to U is just 3 over 7. The partial of X with respect to V is just 1 over 7. The partial of Y with respect to U is -1 over 7. And then the partial of Y, with respect to V is 2 over 7. So here we end up with 6 over 49. I'm missing my number. 6 over 49 and then minus the negative 1/7 times positive 1/7, so plus 1/49, which gives us 7/49 or 1/7. So that's our Jacobian. And now we have everything we need to go ahead and set up our integral. The Jacobian was step 4, so let's put the little 4 right there. And then the integral in step 5. So so according to what I got here, if you had used these to find your Jacobian, you should have gotten 7. And then the reciprocal of that will give you the 1/7. So now our final integral ends up being the double integral over r of 49 x squared y dA equals the iterated integral from, let's see, where is it? -2 to 1, and then from 0 to 1, 49 times now our x. We need to put that in right there and square it. Our x was 3u plus v over 7. So 3u plus v over 7, quantity square, and then times our y, which was 2v minus u over 7, sorry. 2v minus u over 7. And then the 0 to 1, those were v's. Oh, my Jacobian, sorry, I almost forgot about that. The Jacobian was 1/7. So I'm going to put it back here. I could put it up here, of course, but just so we remember what it is, that is the Jacobian 1/7. Now, those were v's and those are u's, so this is dv du. And this is fairly straightforward to evaluate. You could factor out the constants, of course, multiply this out, multiply the entire thing out, and then just go ahead and integrate that way. All right, so I'll stop this video here, and we will continue with 14.8 examples in our next video.